I'm going to talk to you about launching air quality monitoring into the 21st century. This is about developing the TRACE tool for recording and assessing the city environment as a researcher in residence at Satellite Applications and Connected Places Catapult. The idea behind this project is essentially to convert large and cumbersome Earth observations of atmospheric composition into useful information about how air quality evolves within cities around the world. Before I begin, I just want to acknowledge a few really important contributors to this work. As you know, we have gone to a virtual world, and so I'm just showing the research group that I lead. And so we're having our routine group meetings on Zoom. And then also just to acknowledge specifically Kern Vora, who is part of that group, because of the work that he's been doing related to the Research in Residence project. So much of the results that you'll see me present in this work have been developed and analyzed and processed by Kern. There's also many collaborators and contributors to this work, and this is by no means an exhaustive list of logos, but just to acknowledge some of those partners who are involved in this work. Funding support for this researcher in residence comes from the NERC or Natural Environment Research Council, but it is labeled an EPSRC researcher in residence. There's also data providers who provide us with cutting edge research level observations from satellites. And so I'm just acknowledging them here for their contribution as well. The reason that I'm processing Earth observations to convert them to useful information is because that surface monitors are sparse and inconsistent. Here I'm showing you a really ideal case. London is probably the most widely monitored city in the world, and the most widely pollutant that's monitored is NO2. So NO2 is hazardous to health. We have standards that are imposed to regulate NO2. The UK NO2 standard is 35 micrograms per meter cubed, and it's just indicated on the color bar to show that values that are lighter in blue and move towards the yellow, orange, and red portion of the spectrum are above the standard. And so the points that are shown for London are annual averages that are from the London Air Quality Network. The number on the southeast portion of the city shows the number of monitors that are available in 2005 and 2018, two extremes of the record that I'm interested in this work. And you can see that the record is inconsistent. These monitors move, some are redeployed, some are shut down, new ones show up. And so you can't build a long-term consistent record of how air pollution is changing within cities. But what we do have is satellite observations, and these offer global consistent coverage. Some of the instruments that are in space have been there for more than a decade, so we can build a long-term record of air quality within cities. What I'm showing on the left is the observations of NO2 from the recently launched TROP-OMI instrument on board the Sentinel-5P satellite. And this is an image that I could stare at for days, because you can see so many interesting patterns that you would want to explore on a research level, but also in developing products. We can see the evidence of very congested shipping lanes in this image. We can see evidence of open fires in Central Africa and north and south of Central Africa. We can see air pollution hotspots in China, in India, in Europe as well, and to a lesser extent in North America. So North America and Europe have had quite successful air quality policies, and so the NO2 signal from space is actually declining with time. What's great about satellite observations is that the data is freely available. Anyone can access it on NASA and ESA data portals, download it and use it, but it does require advanced skills to process and interpret the data, and often other tools are needed alongside it, like chemical transport models. And we've seen from the recent lockdown measures that have led to dramatic declines in air quality, dramatic declines in air pollution, that there is also misuse of these satellite observations that can often lead to false claims about changes in air quality. And so I'm just showing a link to, and then just the headlines from an article that that spoke about this issue, essentially not using the correct data quality flags to filter out scenes with clouds that lead to large errors in these satellite observations. What's great about satellite observations as well is that they also directly and indirectly monitor a host of air pollutants. We can see indirectly evolving concentrations of non-methane volatile organic compounds, or NMVOCs. We can see sources that lead to large emissions of SOx, so SO2 as one component of SOx, of NOx, NO and NO2, of ammonia, largely coming from agriculture, and then also the secondary pollutants that go on to impact food security, like ozone, which is toxic to crops, and then PM 2.5, which is toxic to us. And I'm not going to take you through a chemistry lesson here, but this is just to show that the precursors we can see from space. These evolve chemically in the atmosphere to form ozone and PM 2.5, or fine particles. And we can see many of these components from space. The satellite record is also extensive. It started in the mid-1990s with the GOME instrument, and is now being sustained with instruments like the Ozone Monitoring Instrument, or OMI, the IASI instrument, or the Infrared Atmospheric Sounding Interferometer, and then also MODIS. In the Earth observations field, like many other fields, we like acronyms. I've just highlighted some of the acronyms of the instruments that are being used in developing the TRACE product. What's also exciting is that it's being sustained well into the future. And we're going to finer and finer resolutions in terms of time and space as well with the next generation instruments. What's exciting is that we have geostationary instruments that are being launched. So these provide us with more than one observation per day. Traditionally, we have LEO, or low Earth orbit instruments that only pass overhead once per day. We're also going down to finer resolution. We started with GOME, which was hundreds of kilometers in spatial resolution, and now we're going to less than 5 kilometers. So we're starting to see finer spatial scales from space. And I do mention that spatial resolution is improving, but it still is a challenge. And this is just highlighted in this image shown here. So the spatial resolution covers quite large swaths of a city. So for the Ozone Monitoring Instrument, or OMI, shown on the left, you can see that 1 pixel from OMI can take up quite a large proportion of London. For MODIS, it's finer resolution, but it's still 3 kilometers by 3 kilometers. So we're not going to see postal code level air quality or air pollutant concentrations. What we're really going to see is the air pollution across an entire city. But this is still valuable information, because we can start to understand how air pollution is evolving across an entire city, to assess whether air quality policies are working extensively, or whether rapid development is leading to widespread degradation in air quality. Vital to developing a tool like this is quality assurance, and this is something that Kern and I have worked very carefully to do, to ensure that the satellite observations are providing us with information about air quality at the surface. The satellites see the entire atmospheric column, and so they have to move through quite a dense portion of the atmosphere to reach the air pollution that's evolving at the surface that we actually breathe in. And so what we did is compared the satellite observations to reliable surface monitors to assess this. And so you can see the sort of tracking of our quality assurance tests in the slide, showing that we've been able to complete quality assurance for all of the components that we're interested in, except for NMVOCs. And the reason this is because there isn't a suitable set of surface observations for validation, not even within the UK. For something like SO2, it didn't pass quality assurance. SO2 is very challenging to see from space using UV visible spectrometers. It has very poor detection, so you can only really see unregulated coal-fired power plants, for example, very, very large point sources. And because in the UK, the power plants have been very carefully regulated, the SO2 emissions coming from these power plants is now quite low and below detection of the instrument. And just to highlight that this research has been reported in the peer-reviewed literature, it's currently undergoing peer review, and you can see a preprint of this if you're interested in finding out more. Just follow the link shown on the slide. We also use statistical techniques to estimate the trends in air pollutants in our cities of interest, and also assess whether these trends are significant. So I'm just illustrating a few examples here. For developing the tool initially, we targeted London and Birmingham in the UK, the 2 largest cities in England. And then Delhi and Kanpur in northern India. Delhi, of course, is a large city and undergoing rapid development in India. Kanpur was of interest because it was highlighted by the World Health Organization as having the poorest air quality of all the cities where there are air quality monitors. And so you can see in this demonstration slide that we have a significant decline in NO2 in London and Birmingham of similar magnitude, demonstrating that air quality policies targeting NOx sources has been successful, whereas in Delhi and Kanpur, if we look at AOD, or aerosol optical depth, which provides us with a proxy measurement of PM2.5 or fine particles, there's a rapid degradation in air quality. So AOD or PM2.5 is increasing by 2 to 3% per year in both of these cities. And this is related to rapid development, large PM2.5 sources, and also absence of evidence of successful air quality policies, where air quality policies have been implemented in Delhi, but we're not seeing evidence of that in the long-term record. And so this just puts everything together for all of the air pollutants that we're monitoring from space for London, Birmingham, Delhi, and Kanpur. These arrows are colored by increase in red or decrease in blue, bold for significant trend, not bold for not significant trend, and then just the size of the arrows indicating the size of the trend. And you can see for London and Birmingham, NO2 and PM2.5 have decreased as we would expect from successful air quality policies, whereas we're seeing the opposite in Delhi and Kanpur. The NO2 increase in Kanpur is not significant and quite small. And ammonia is an interesting compound to assess. Most of it comes from agriculture, and we're not seeing any significant change in ammonia in any of these cities. And this is consistent with what we would expect. There are no air quality policies directly targeting ammonia. And so now that we've quality assured this product, we've tested it over cities where we know more about air quality policies because of previous research that's been underway, we now move to a sort of uncharted territory, tropical megacities of the future. And so the reason we're looking at the tropics is multiple. Two main reasons is because this is a region of the world that's undergoing the fastest rates of urbanization. And so by 2100, most of the largest megacities will be in tropical Africa, for example, because there are other formidable cities in the tropics that are of interest, but Africa is of particular interest because of the rapid population growth. Another reason is that this is a really large air quality data gap in the world. And so this is just highlighted with one example data set that's being provided by OpenAQ, and this is a really valuable resource if you're interested in using air quality observations from surface monitors. They essentially host publicly available data like PM2.5, NO2, ozone, many other air pollutant data sets. But this is just to highlight that the tropical band is really where we have an absence of data. And this is really concerning because of the changes in air quality that are forecast to take place in tropical cities or megacities of the future. And so what we've done is we've applied the same trend and statistical significance analysis to the air quality, to the tropical megacities of interest. And so you can see the results illustrated here. And so just to take you through some of the features of this plot. So the trend or the size of the trend is indicated by the color. So if it's a warm color, it means that it is an increase. If it's a cooler color, it means that there's a decrease. The size of the circles indicate the baseline NO2, so the NO2 at the start of the record, just to give you an idea of where this sort of increase is starting from. So that just shows us that in Africa, NO2 concentrations are quite low at the start of the record compared to in India and Bangladesh, where the NO2 concentrations are already quite high. We've also indicating significance of this trend. If there's a big bold circle around them, it means that the trend is significant. And so I've just highlighted two regions that are of interest here. We can see that in West Africa in general, there's an increase of between 1% and 5% per year, quite dramatic increases. And then more so in India and Bangladesh, where we see that the increase can be anywhere between 1% and 14% per year. One city, Jakarta, does stand out as notable because it's undergoing quite a significant decrease in NO2, indicating that there are effective air qualities in Jakarta compared to the other tropical megacities. We've also done this analysis for PM2.5, as well as ozone, as well as NMVOCs and ammonia, but those aren't shown here. For PM2.5, we don't see as clear an increase in West Africa as we did for NO2, but we do in India and Bangladesh, where we can see increases of between 3 and 8% per year, really dramatic increases. We think that the sort of absence of a significant trend for West Africa might be because of such a large contribution of seasonal open fires or burning of biomass in West Africa that masks the trend from anthropogenic sources. So I've highlighted some of the work that's underway in developing the TRACE project, in applying it to 4 test cities, and then expanding it further to the undersampled tropics. But this is just a slide to highlight some of the other projects that are underway in my research group. We're working with the Leicester City Council to try and characterize the PM2.5 sources in Leicester. So that means local sources, as well as neighboring sources, and then more remote sources, perhaps mainland Europe, the contribution of mainland Europe to PM2.5 in Leicestershire. I'm also working with DEFRA and using the geochemical transport model to obtain estimates of ammonia from the EASI sensor. And this is going to be used to test the UK National Atmospheric Emission Inventory of ammonia, which is very challenging to estimate. And then I've also been awarded an ERC starting grant, and the project is called UpTrop. And in UpTrop, I'm developing new products of NO2, most notably focusing on the upper troposphere, so about 8 to 12 kilometers overhead from the TROP-OMI instrument. And I've just indicated a web link to find out more about that project. There's other projects underway in my research group, and if you'd like to find out more, you can follow the link on the slide. Thank you very much for your attention.